So we will now look at the other case where aliasing is expected because the sampling frequency is smaller than the Nyquist sampling rate. So let's actually look at that in detail. We're looking now at case B, where omega s, which is given to you, is not larger than 2 omega naught, and in particular omega s is equal to 2 over 3 omega naught, implies that omega s so I believe we had 3 over 2 omega naught, this omega s is 1.5 omega naught, and this is less than 2 omega naught. So in here, aliasing is expected, and this is basically loss of information, and then you also expect that the original signal cannot be reconstructed. So let's see this carefully. First, we're going to plot x of omega, and this is no different from the case before. You have minus omega naught and you have plus omega naught. It's no different from the case before. Please note that for the time being, we are not really worrying too much about the y-axis. When you have a filter, you can also amplify the signal and change the y-axis to match how things should be. Aliasing is really connected to the x-axis and the problems that occur when you don't have high enough sampling rate. So this is your very standard cosine function. This is the bandwidth. Because this is plus omega naught, there's only one frequency in it, and that is the highest frequency, and that becomes your bandwidth. Now, your sampling signal, which is this p of omega, is separated with each other by omega s, and omega s in this case is 1.5 omega naught. So this is 1 and this is 0.5, and this is omega s equal to 1.5 omega naught, and this over here is also omega s, and this is going to be minus 1.5 omega naught, and we are just going to look at these three terms and not worry about these other ones. It's all repeated. Now xp of omega is equal to, or is rather I should say proportional to, x of omega convolved with p of omega. So this convolution is between this signal and this signal. What you're going to do is that you're going to take every possible delta function here and convolve it with this signal, and you're always going to get this signal back again. So you first convolve this one with this one, this one with this one, this one with this one, and then you add all of them up. That is what gives you the final answer, xp of omega. So what you will do when you're doing this is you have to be very careful, because there is a loss of information, as this one is not far enough away. The sampling frequency is not high enough. So let's first draw this case. This is minus omega naught, and this one is plus omega naught. So that corresponds to convolving with this signal. But when you try to convolve with this signal right here, this is 1.5 omega naught. You try to convolve with this signal. I'm going to just plot this in a dashed line over here so that you can understand where it's coming from. And you look at the dashed line, and then you see that this is your central frequency is 1.5 omega naught, and you are going to get two lines at 1.5 omega naught plus omega naught and 1.5 omega naught minus omega naught. So 1.5 omega naught minus omega naught, this gives you actually 0.5 omega naught, and 1.5 omega naught plus omega naught gives you 2.5 omega naught. The exact same things happen here as well, that you will mark this minus 1.5 omega naught, but when you convolve this one with these two, you get this signal back again, but at this point, with the center at this point. Now when you have the center at this point, this is just half omega naught. You are going to get this one, and let me just draw it with kind of points so that you know that this one is slightly different. And this one is over here, 0.5 omega naught. This is 1 omega naught, this is 1.5 omega naught, and then you have this kind of, let me just draw it here. So that corresponds to this particular convolution. So you clearly see that things are getting messed up when you have xp of omega. And there's actually no way that you can filter this carefully. If you try to filter just this stuff here, you're going to capture this. If you try to filter this entire thing, you'll capture these two things. So clearly you can see that this is xp of omega, this is the spectrum, and you can clearly see that aliasing is happening. And you will see that there are these extra features which will definitely cause loss of information. So now the next step, let's do this. The next step is filter. So you take xp of omega, and you pass it through a low pass filter, and you are supposed to get x of omega, but I'm going to denote this x tilde of omega because we kind of know that it's not really going to work. Now if you do your low pass filtering, no matter how you choose, let's look at this again, no matter how you choose your filter, either you get no signal if you choose your filter too small, and if you choose your filter between these two things, low pass filter, you're actually filtering just this stuff. If you choose your filter over here, then you are dealing with two cosine signals. So no matter how you do it, you cannot recover the signal because of loss of information. And then you have essentially kind of low pass filter gives you plus 0.5 omega naught and minus 0.5 omega naught. And the reconstructed signal, this is x tilde of omega. The reconstructed signal x tilde of omega is not equal to the original spectrum, and x tilde of t, this is the incorrect reconstructed signal. Due to aliasing, and this is equal to cosine of omega s minus omega naught t. In this case, it becomes equal to cosine of 0.5 omega naught t, and this is not equal to cosine of omega naught t. So the reconstructed signal is clearly not the same as the original signal, and that's because of aliasing, and this is essentially a low pass filter that was used in the last step. So I hope that this example clarifies the concept of Nyquist sampling rate, as well as the concept of aliasing, and I'll remind you that this is because omega s is smaller than 2 omega naught. The Nyquist sampling theorem states that you have to have the sampling frequency larger than 2 times the bandwidth. But here you have the sampling frequency to be less than 2 times the bandwidth, causing an error in the reconstructed signal. Thank you.